Welcome to Mama's Casserole, the podcast where business meets a little bit of everything. I'm your host, Zach Romero, serving up a hearty mix of insights, stories, and surprises. From strategies to grow your hustle to the latest tech trends, current events, and even a dash of conspiracy theories. There's always something bubbling in the oven. So grab a plate, pull up a chair, and dig into Mama's Casserole. Let's dish it out together. All right, today on Mama's Casserole, I'm thrilled to welcome a true pioneer in the realm of space exploration and advanced infrastructure, Dr. Pete Swan. Dr. Swan is a leading authority in the field of space elevators and serves on the board of the International Space Elevator Consortium. Pete has worked with organizations like NASA and DARPA, contributing groundbreaking research that brings us closer to making the once impossible concept of a space elevator a tangible reality. Beyond his technical expertise, Pete is an author, educator, and a passionate advocate for the future of space infrastructure. His work not only challenges how we think about getting to space, but also how space could become accessible to all. So today we're going to dive into the fascinating science behind space elevators, the hurdles we still have ahead of us, and how this technology could revolutionize everything from satellite deployment to deep space exploration. So Pete, it's an absolute honor to have you on the show.
Well, thank you very much. I enjoy talking about space elevators because it has such a great potential for humanity. I truly believe that we need space elevators. It's not a choice because of the facts I'll discuss in the following 20 or 30 minutes. The kicker is the space elevator is revolutionary and it transforms the way we get to space. Let me just use a basic concept so that we understand it, and then I'll show why it's so critical we proceed. The methodology for a space elevator is you take a 1 meter wide, 100,000 kilometer tether, and you unreel it geo, and you roll it down and you roll it up, and then you end up with a 100,000 kilometer long bridge. It's anchored on the bottom at the spaceport called Galactic Harbor, and it's just a oil derrick with a big reel on it. It's simple. And then you have this long tether. The material is what's been holding us up for the last 125 years since the original concept in 1895. So the material is now out, and it's been produced in many different forms. And the one that I like is it was made a 0.5 meter sheet, 1 atom thick, 1,000 kilometers long. And it was done in South Korea, so it's a global rush to get this material out. And the material is going to change the industry, the space industry, and so many others, because the material is indescribably strong. It is unbelievable. And it's coming out of the lab now, so it's really neat. So that's the tether segment. We got the earthport segment. And then we have the tether climber, which goes up and down. The concept is simple. You have a thin tether, 1 meter wide. You put wheels on each side. You put pressure on the wheels so they're sticky on the tether. You turn the wheels, friction, and it goes up. It's that simple. So your tether climber goes up and down, and then you get to the geo arena where we'll have a spaceport of some type where we offload, onload, and all that kind of stuff. And then we keep going to the anchor at the other end. We call it the apex anchor. Now, the apex anchor has the principal role of providing stability. Now, this particular architecture is extremely stable, but we have motion induced by the silly thing called gravity of the sun and gravity of the moon and things like that. So we have motion, but it's not very much, but we want to, use it to our strengths. So that's the main purpose of the apex anchor. But we just finished a study at the International Space Elevator Consortium, 2 years worth, which defined the missions in addition to stability. And there's such remarkable things like transportation, like 14 hours to the moon, 61 days to Mars, and we can release every day of the year toward Mars. Now, some trips will take 400 days, but who cares if it's hammer and nails? And so we have a whole bunch of revolutionary missions at the other end, the top end. Now, how does this stay stable? How does it stay out there? It's a simple physics thing. If you take a rock, put it on a string, and run it around your head a whole bunch of times, and then release it, it takes off at a high velocity. But the key point that I want you to understand is, as it's going around your head, it's stable, and it keeps the string taut and
Right.
straight up. And so that's all it is. It's basic physics, and it's been shown to work a whole bunch of times. So we're really confident that the concept is really solid. So now let me give you just one little benefit of a space elevator. The rocket has a problem. The rocket has a rocket equation, which was done in the 1890s by Tsiolkovsky, and it defines the delivery efficiency of a rocket. And it turns out that we've done the best we can with chemistry right now, and you don't go to those other ones like ion and nuclear when you're going through the atmosphere. So we're basically at the top end of rocket performance. They deliver 4% of the pad mass in Cape Canaveral or wherever to low Earth orbit. It only provides 2% to the very productive orbit called geosynchronous, and it only provides 0.5% of the mass on the pad to the surface of the moon. Apollo 11 delivered 0.5%. So if you ask anybody who makes money in transportation and you tell them I have a system that'll provide you 0.5% to a location, they're going to laugh in your face. They're going to say,
Right.
that's silly. I like to put it a different way when I'm talking with students all the time. If you load one car, you buy a car from Japan, load one on a ship, container ship, run it to LA, run the car off, and then you take that ship and you move it over to Catalina and you sink it. That's the concept. It's really hilarious. But I love rockets. I mean, I've been to Apollo 12 launch. I've been to whole. Rockets are fantastic. They do what they do, and we want to be partners with rockets.
Right.
Because as space elevators, we really have trouble with humans until we get like redundancy and two tethers together and stuff like that. So we're going to be logistics only for the first 10, 15, 20 years. We want to partner, let rockets move people through radiation belts fast. So we really love rockets, but they have their basic flaw. And what the space elevator does is provide 70% of the mass on the top of the ocean to geosynchronous and the lunar orbit. 70% versus 2% to geo and 0.5% to the surface. So we're talking about 140 factor in efficiency of delivery. So that just describes the basic concept of a space elevator in the sense of we need it to move off planet. We need it to do support to Mr. Musk. He wants 1 million tons to the surface of Mars. Now let's consider it 0.5% delivery by his system. How many launches is that? That's a lot. And it take a long time. Whereas if we can deliver that, 70% of our pad pickup goes to Mars, then our efficiency is so much greater that we can do it in like 7 years. I've done the numbers. You guys can help me with that if you want. But it's kind of a remarkable comparison. And Mr. Musk is going to Mars. There's no doubt about that. And he needs 1 million tons of logistics support. Ouch. When you're
Right.
doing rockets.
Well, I did the math before we came on these numbers, and to kind of put that into reality, at 0.5%, for every 1,000 pounds we try to send off, we're getting 5 pounds.
Yes.
Versus the 700 pounds of that 1,000 that a space elevator is going to deliver.
Correct.
I mean, that to me put it into perspective, like of 1,000 pounds, only 5 gets there.
I know. It's remarkable. Now, I love rockets, and Mr. Musk, I can't say anything about him except phenomenal in the business, in the arena like that. He has remarkably changed the space business. My wife and I teach here and there, and we really call that the commercial imperative. The commercial world is coming out and saving humanity. It's helping us get to planets. It's helping us put solar power satellites up to save the Earth. It's helping us do weather. It's helping us do. Rockets are essential, and we really need them, and we love rockets. But we're proposing the next generation, the evolution to an avenue to space, and we really truly believe we can do it. Starting about right now, it'd be nice to have some funding and get going, and we can do that. There's some other interesting characteristics of the space elevator that they don't even mention in the rocket arena. The first one is we call our avenue to space, the bridge to space, as a green road to space. We don't burn anything in the atmosphere, so we're not destroying the atmosphere. And you got to look at the numbers; it's scary with rockets. And then we raise it up with electricity, so we're not leaving any debris behind in low Earth orbit or anything like that. So there's no debris from our system. And we enable systems like space solar power, which are very, very good environmentally in lowering the need for electricity burning in coal plants and stuff like that. So we truly believe the space elevator is a green road to space. We like to talk about that because we can impact the climate, the environment, et cetera, by enabling this transformational infrastructure.
So that kind of brings up a question when you talk about space junk or whatever that you guys leave behind. But one thing that I did a research paper on this a number of years ago. That's why I've been following this topic ever since. But one of the things that was brought up consistently was the existing space junk that's up there, or traffic, whatever you want to call it, in orbit with all the satellites. But you're a fixed point. I mean, is that going to have issues with junk that's already up there hitting the elevator, hitting the track? Is that an issue you guys are going to have to deal with?
Yes. It turns out there are a lot of issues. Okay. We
Yeah.
have issues all over the place, but it's a mega project. And you enable mega projects. By the way, that's defined as over $5 billion in over 10 years to develop, something like that. A big infrastructure. And there are issues we have to deal with. And let's address this one right off. But let me give you some credibility first before you start laughing at my answers. I actually tracked satellites for a year. And so I was in the whole arena of understanding the debris density, the debris stuff. I've worked with the debris office in Houston, NASA debris office in Houston, off and on for the last 40 years. And I've written papers on space debris and space elevators and all that kind of stuff. And we have two significant studies, 24 months the first one, about 12 months the second one, on our website. It enhances the body of knowledge there, because what it does is it addresses the probability of impact. You mentioned it. There's a lot of stuff up there, will be a permanent infrastructure, stuff like that. There are about 6 or 7 steps we need to take to be operational within the environment. But let me give you some just real quick ideas of what we did. The first study we did in 2010, obviously it was one of the first issues we wanted to address when we created ISIC. So it was the first official study research report we did. What we did is we looked at the population of environment up there, and we put a 1-meter tether straight up, analyze what is that cross section for interface between 200 kilometers, which would be the bottom of the debris, and 2,000, which would be the top. And then we did the probability of impact of all the debris. Of every piece, we calculated the probability of intersection. And it was really kind of eye-opening to see how little impact there was. We would have to move the tether about once every 7 days, 8 days, to maneuver out of the way of the big things. Now, the small things, we don't have to worry. Most of the stuff's going to bounce off, and there's stuff that might not bounce off, might go through, but then you just patch it. We're going to have tether patchers, tether climbers going up and down, repairing and stuff like that. So we don't believe that much will puncture a hole in it, because the material is so flippin' strong. It's unbelievable. And one of the questions we always ask our tether guys is, does it rip? And the material we're looking for doesn't rip. In fact, it actually repairs itself. So it's kind of interesting. But Then we did a study in 2019, 9 years later, same approach, same topic, everything else, except we took NASA's data from Houston on the density of the debris, did the same calculations, and it was linear, just like you would figure, more population. And so we did all the population numbers, probability of intersection, all that. It's in there. Now, here's the kicker. NASA at that time was very interested in Mr. Musk's Starlink and the other competing constellation of satellites in low Earth orbit. So they projected density of debris in 2030. So we literally have done the numbers for 10, 19, and 30. And we still come with the conclusion we can operate in the environment that will be there. Now, there's 3 or 4 things that we need to do. The first is we go to 2,000 kilometers and we bring down 3 or 4 legs. And so we have a principal leg doing, but we have 3 other backups. So if one of the legs is punctured, which we don't think will happen because we can move them all, we don't think it'll happen. But if it happens, you still got backups. So, you're in good shape because you've got 3 or 4. I like the number 6, but most of the people say like 3 or 4. That's the first thing. The second thing is we have to have the space elevator core people knowledgeable inside the space debris operational centers. They call it traffic management. We want to have our people there, and we need some of their people in our place. So we've got operational approaches to work it. We've got physical repair. We got physical deployment of 6 legs, et cetera, et cetera, et cetera, et cetera. We've really worked this problem pretty hard, and we really believe we can be operational in it, which would then enable all the transformational characteristics that we talk about.
Yeah, no, that's great. And so listeners, I know they're trying to probably picture some of this, but we're going to post some pictures on our social media when we do post the show, a link to the consortium's website so everybody can really see that body of work and see how far they've really come. But I guess one question I have too is, how is the consortium like? Are you guys collaborating or trying to collaborate with like governments? Is it tend to be more private companies, or is it still just like research institutes at this point?
Okay, you ask multiple questions here.
Right.
Let's start with, I truly believe that we're going to have global competition, and it's going to be commercial space elevators. Our concept at ISIC is we support everybody, and we go to conferences and stuff like that. We're a consortium. We're like AIAA or IEEE or the American Medical Association, where
Right.
we help everybody. And so we're looking at people that really would like to start a space elevator construction project. And we've had offers and we've had people thinking about it, but that would be a commercial company, not inside there. Now, Kathy and I created what's called the Space Elevator Development Corporation, and we're just now forming and getting going. We don't have a CEO, we don't have a treasurer, we don't have anybody like that, but we need funding, and then we would start a company. So I believe we're at the phase where we really need to start a corporate company. And there'll probably be one in China, and there'll be one in Europe, and there'll be competition, because the one who gets a transportation infrastructure up that delivers hardware to space will basically dominate the future of mankind moving off planet. So we believe we're going to have 6 space elevators around the equator through competition, maybe 3 pairs or something like that. Each corporate entity would have one up and one down. But then I always kind of chuckle and say most of the money in the early days is going to be up, so we'll probably have 2 up.
Right.
But we're having one little announcement to make everybody happier. We're having a session at the International Space Development Conference, the National Space Society Conference in Florida in October. It's June in Orlando. But the key here is we brought up the point of bringing stuff down. We're going to have a technical session discussing that with 2 papers at least. And then our panel discussion will be asteroid mining efficiency of return, and emphasize that if you bring it over to the space elevator, you automatically have boxes or tether climbers, whatever you call them, to bring stuff down. So literally, we can bring stuff down, and you don't have to go through that 25,000 mile an hour impact of your resources going into our atmosphere and trying to land and be safe and all that kind of stuff. So though the bringing back of the asteroid uh, valuable products, what they mine, is going to be a topic for discussion in June, which should be interesting. I'm looking forward to it. I've got my own ideas, of course, because I keep coming up with little ideas, but it's an intriguing arena that everybody wants to go make money on asteroid mining, and of course, much of it will be used in situ around the asteroid and on the moon and on Mars and stuff like that, or spinning habitats. But there are a lot of people that say your big money is bringing platinum from an asteroid back to the planet, assuming that's your most valuable asset. I don't know how that works, but
Right.
but it's a fascinating arena of how do you make money when you mine asteroids. And if you want to bring it back, the space elevator is a good option.
Have you guys done like a cost analysis at this point on building the space elevator, or is the graphene still a little bit too early to be able to put a cost on it?
No, I've estimated. I think it's about $18 billion to do the whole thing and have two space elevators in parallel going up. And then it's going to get cheaper per elevator. So, that's the development cost and all that kind of stuff. And then you have lifetime costs and operations costs and all that. And it builds up. But basically, if somebody had, $2 or $3 billion now, we could really take the tether material to production. And I think you could probably get started with like 30 or 40 million. So, the point is that we really need the money to get the tether materials down to a reasonable cost and a production line. I keep asking the questions, how many rolls of toilet paper are we putting out today?
Right.
Or aluminum foil or saran wrap and stuff like that. So our industry understands how to roll things up. Now, it'd be a little more interesting when you're talking about a single layer, a single atom layer. But the answer is we've got really smart people out there that'll figure it out. And the tether is so light that it should be able to be produced. And that's the way they're doing it today. They use carbon vapor deposition. I'm not a chemist, so I don't know all this stuff. But you put the carbon in a gaseous form into a real hot furnace, and the atoms break down from the molecule, and the hydrogen floats off, and the atoms of carbon are left on the surface of copper. And then as you form that, and it forms up to one layer, you then roll it out of the furnace and take it off of the copper, and you've got your material. So the discussion on how to do it is kind of interesting and remarkable, and they've been doing it in multiple countries around the world. So we're getting there. Now, it turns out the interesting thing about graphene is it comes in different forms, and recently there was $1 billion contract for graphene in the Asian market. Now, they were getting that for improving concrete by 20% strength, 20% lighter, cools down 20% faster. It really makes a difference in the concrete. That's a big move on graphene. Well, that'll spill off into the next two phases of sheet graphene, and they're starting to get into that too. So there is some really hot research going on right now in graphene because it will make a difference. Let me give you a simple example. It is so flippin' strong you can't even calculate it. People have trouble comprehending the numbers. Why don't we have an infrastructure project to wrap all our struts on all our bridges in the U.S. so that we don't have to go redo the big columns that are supporting? If you put this material around the columns are not just going to stay there. The weather's it won't affect them and everything else. So my idea is there are so many infrastructure projects around the world that would be benefited by an extremely strong, light, flexible material that it's remarkable. So graphene is going to take off remarkably in the next decade, and so we want to take advantage of that.
Right, and that kind of segues into a question that I want to get into, and this is part of why I've been so interested in the space elevator, specifically in other projects, is it harkens back to the days of the space program in the 60s and all the benefits that come of a mega project. And that's basically what you're touching on now is with this graphene, there's so many side benefits and there's offshoots of technologies that are always developed to try to answer another question. right? And so, hence the Velcro or freeze dried food for the astronauts. All those kinds of stuff do a spin-off, right? So you're already touching on that with the graphene. We've got some infrastructure projects. We've got who knows what anything else somebody could dream up that graphene could be applied to. And I think there's just something about a mega project that even a country in general needs for pride, for motivation, and just to spur more technology. And that's one of the reasons why this topic and this subject interests me so much as well.
I agree with you completely. The spin-offs are going to be remarkable, not only on the material, but the ability to go to space and take small satellites up to, not Leo, but take them all the way to Geo or to the moon or something like that. The ability to launch every day toward Mars is a remarkable capability. The difference is that when you're lined up with the two planets, you can go as fast as 61 days a few times, but it averages about 120 per trip. And that's like, what's that, 4 months versus 7 or 9 by rockets.
Right.
And
Right.
they have to wait every 26 months before they can go because the window only opens up. Whereas we can go by Venus, we can go, if you're not sending people, you can take a 400-day trip. So the ability to take and do that is remarkable on the spin-offs. What can we do? How can we improve? I recently, well, maybe 2 years ago, gave a little lecture at the University of Manchester where they won the Nobel Prize on graphene. They discovered it, the physics terms about getting a Nobel Prize, all that stuff, well beyond me. But anyway, those guys did that. So they have a thing called the GEEK. That's the Graphene Engineering Innovation Center, I think. But they have a great place. And so I was out there looking at what they were doing. So they asked me to talk about, well, if we get this stuff, what can we do with it in space? The bottom line is satellites will be about a quarter of the mass today. The rocket launchers will be a quarter of the mass today. This stuff works works with cryogenic temperatures. So you can put the cryogenic fuels in it and stuff like that, and it'd be lighter and everything else. So the tremendous advantage of a light, strong material would be leveraged by rockets. So rockets will be improved as well as spacecraft and as well as other industries, automobiles. I think, the Mercedes hood is going to be a big product. It's light, sexy, good looking. And
Right.
then, what about airplane wings? It won't rip. It won't rip off. The airplane wings are going to be made much stronger as they're being made lighter. And so it's less fuel, et cetera, et cetera. So we're talking about a material that's going to change the world. It's like in the 50s, there was a movie about it, and everybody was gaga over plastics. What's this plastic stuff? And that changed the world, all the packaging and everything else. And now I think that we're going to have a similar revolution across the board on all industries, on all topics, on graphene. And so, yeah, the spin-offs from the space elevator will be remarkable.
On the graphene, though, where you're saying it could change things, which I totally see what you're saying. Now, is there an ability to recycle graphene? Do you know?
It's just carbon is going to be put in a solid thing. So we're really talking about we should be getting a green award from the world because we're taking so much carbon out of the atmosphere to make these tethers.
Mm.
Yeah, so we should get enumerations of funding for doing carbon removal.
Right.
But in the overall sense, we actually had the topic come up at a discussion in Scotland, a month ago, 2 months ago. And the question was, are we making a material such as asbestos, which would kill us? And the answer is, by some really good chemists, that the carbon would basically just be another part of your body. It would flow through. And so if you breathe it or whatever, it probably would not cause those types of issues. Now, I agree that a powder of any kind, you don't want to sniff it. So having a mask on and stuff like that will be routine for the process workers that are working with the materials. And, we'll protect our workers and all that kind of stuff. But once it's made into graphene, it's a solid material. So, we won't have those types of issues, I don't think.
I've got like three kind of parallel questions, but a little bit. So far, with you working with the space elevator, what has been the most exciting moment for you so far and what you've been working with, what's been accomplished?
I think the most exciting moment was the realization that we have the material, and that was really 2 years ago when Dr. Eddy and I went to the Graphene Engineering Innovation Center, the GEEC at the University of Manchester, and they had sticking on the wall just leftover pieces of graphene, the full-blown single crystal graphene just stuck on the wall. We're finished with that piece. We've tested that piece. Let's put it up here. And they had stuff like that all over the laboratory. Some of them were really small. Some of them were like a half meter by a half meter. And, and you're sitting there saying, what's that? Oh, that's we did that like 6 months ago. It's a true piece of graphene sheet, not on copper, just alone. You're sitting there saying,
Right.
For me, it's like magic. And those guys are chemists. They're doing that stuff all the time. And it's kind of like trivial. So they put it on the wall or something. And it's really amazing. But the realization that the chemists were working on it and just trivially tossing out little pieces here and there made me understand that the material is pretty close to being really remarkable. And we could start doing production of some of this stuff.
Well, and that's got to be because when I did my research paper 15 years ago or so in college, the carbon nanotubes were the big thing that they were pushing, and because the strength is there, but the production isn't there. It still isn't there today at all. So to be able to have a revelation of finding that there is a product or a compound out there that'll work had to been like, oh, hey, we're on the right track. That had to been exciting for sure.
Well, I want to make sure you understand. Carbon nanotubes have been a miracle material. They are doing marvelous stuff. I mean, they're doing anodes and cathodes and all kinds of jazz, and their very small characteristics are excellent in the materials, that the composites and stuff like that. They are really a miracle material, and they're doing well across the industry. And I really applaud carbon nanotubes and hexagon boron nitride nanotubes and stuff like that. But the promise they had of making a long, strong material is not there. They have not done that. And so if they do that, I don't mind using carbon nanotubes. I mean, if they can make it work, I'll use theirs. I'm a system architect. I want a material that will be easily produced, inexpensive, and make really long segments. My concept is it would really, really be great if we had 100,000 kilometer long, 1 meter wide molecule, one atom thick.
Wow.
That's what the objective is. And then you put 12,000 of those on top of each other with a capability to be, high friction so they don't slip. And that's our tether right now for the loads we're talking about. Remember now, this is a mega project. We haven't even gotten funded yet. So these are preliminary engineering and scientific answers. But the objective is to have 100,000 kilometer long tether that's strong enough to do all this, which means, you got to be more than 26 gigapascals, and we would like more like 100. And we've measured the graphene up above 100, and we've measured not the single crystal graphene, the superlaminate graphene, but the regular polycrystalline graphene, which is one step below and producing. That we measured up to like 60 or 70 gigapascals, which would be, a safety factor of like 2 or 3. So that would be good also. So we're moving fast on that stuff, and it really is remarkable.
This should be hopefully a little fun question for you. If the space elevator was completed tomorrow, what would be your personal dream mission to see accomplished first?
Well, I'd like to go up to the honeymoon hotel that's going to be up at 250 miles up.
Right, right.
You remember I mentioned like 6 tethers coming down? I
Yeah.
figure one of them would be an up and down to a hotel,
There.
and we're talking about serious, beautiful views up there.
Oh yeah.
And it would only take like 4 hours to get up there, on a tether climber, 100 kilometers. You wouldn't be going too fast or stuff, and you'd have humans and all that stuff. But it turns out that the mission I would like to see really implemented because of the space elevators is space solar power.
Mm.
We and I'm doing this from the energy side. Everybody argues about the goodness and CO2 and all that. It turns out if you look at the population growth, it's really humongously growing around the world. And in Africa, it's going to double in the next 15, 20 years. I mean, double. And we're talking
Right.
about twice as many people, and the resources are not equally spread around. And so we
No.
have a tremendous amount of people that do not have access to electricity, and thus they can't keep their beer cold, or they can't keep their meat fresh, or they can't get their eggs. They don't have electricity.
Right.
And what
Right.
happens is the Space Solar Power Program is a remarkable one that's being motivated by two forces. One is lower the carbon impact and also energy. But the energy is what's going to fund it. And everybody's talking. Let me use an example. The UK is leading right now, and they even have a contract from. I'm thinking Iceland, Greenland, Iceland, Greece, Iceland. I think it's Iceland. They have a contract to supply electrical energy from space. Now, it's long term, and it's a firm fixed price they're going to pay, but they're not paying much. It's just an initiative. But they have a contract to supply energy to Iceland from geosynchronous. And
Mm.
so they're going off. They've got a very good design. They've got all kinds of activities that are going on. And then, I'm a stick in the mud when I get to those meetings. I say, we'll be there. But let me ask a question. Are you pointing any beams south? They put this thing up there and they have a contract with Iceland, the UK. I mean, it's being built by UK, so you got to get energy to the UK. But is anybody saying I'm going to point a beam south? I'm not saying give the energy away.
Right.
I'm saying ship it south and charge them for it. But the kicker is the developed world would be providing a capability called electrical delivery.
Yep.
And we don't have to build things down someplace. We just provide a receiver down there and they put it near a village and they share the power. And so the idea of a conglomerate building phenomenal energy sources from space called space solar power, they're going to be able to take care of their customers. But should they increase the customer base by looking south of the equator as well as north? And every time I say that, they say, "Oh yeah, we'll take care of that." But I say, "Wait, where's it in your plan?" Because if you don't have it in your requirements for the design of the satellite, all the beams are going to be north. All the hardware focused antennas are going to be looking north. And so, yeah, you could turn it around and then they all look south, but then you don't have the revenue you have when they're looking north. So my point is, let's put some antennas pointing south as well as north. And I think that would really help. And that would be a mission that would be really worthwhile to be accomplished by space elevators, which is supply of electrical energy around the globe, wherever it should be going and needs to be going. Electricity away. But we don't have to build coal plants someplace. We don't have to put nuclear power plants in developing arenas. We just put electrical collectors and the energy is distributed from the download spot. So, I really think the space elevator principal purpose in the near term should be providing electrical power around the globe.
Yeah, I love that. Like, I hadn't thought about that. I do remember reading kind of the other direction is the original idea to power the climbers was to beam power at the climber to get it to climb, but it hadn't even crossed my mind because I hadn't read about it, beaming power back down to the earth for, energy.
Base solar power is a big program. You ought to have somebody on your podcast to talk about that.
Yeah, that does open up a whole other topic for sure. I mean,
no,
hadn't
it's
even crossed my mind. Yeah.
Well, you can look it up. It's got a lot of research out there on it, and it's a really viable program. It has technology in there today. The flaw is everybody keeps saying, well, we'll use rockets, and we've described the 2% delivery to geo.
Yeah, so let me finish up with one last question. As I mentioned earlier, I am going to post a link to the consortium website and those type of things. We're going to put up some graphic images of some of these things we've tried to explain on audio. But besides that, is there a way for the public or private sector to get involved with the consortium?
Yes. The first and the easiest thing is to go on our website. At the bottom of the first page, the home page, is sign up for the newsletter. Once you've done that, then you're going to get a monthly newsletter that has a lot of information on it. It has a monthly input from the graphene people. So you can go through the archives and get a real fast education of the graphene, how it's developed over the last 2 years. And then we have a little note from the president and stuff like that, and announcement of meetings and all that. That's the first thing. It's easy. It doesn't cost you anything, and it's simple. The second is we would love you to join us, student member, all that kind of stuff, and that would help. But then the third thing is we do have research projects going on, and they're talked about in the newsletter and on the website. And so they would be beneficial if you're interested in participating. Right now we have one on power to the climber. So if anybody's interested in lasers or RF or solar or whatever to power the climber, we have one on the simulation. So we've got, actually it's broken into two studies. One is the general simulator and the other is other stuff. But we've got, anybody who's a computer geek and wants to get in and support software development, we've got a big project there. And what you would do is send on the info stuff, say, I'd like to join the study team on such and such, and we'll get back to you and make that happen. But it turns out we have research. But then there's 2 or 3 other things. The first is we have intern programs over the summer. And deadline is 1 April. And if you could advertise that, that'd be great. But basically, we pay them $599. Now, I wouldn't want to say that's $1 short of all the paperwork, but if you're $599, we could give that amount. And then you work with a mentor and do a project. And the projects have gone the whole spectrum across support to space elevators. We haven't done political yet, but we've done almost everything else. Some hard engineering, some architecture, some software, some building stuff. And we've had some pretty good reports by the students over time. And it's, you basically start putting your research proposal, you get a mentor, then between about mid-April, May, you start, at the end of the summer, you do a research paper. And then we allow you to present them at different places so that we get the word out. So that research topic by an intern is really pretty neat. And then we have an academic challenge, which is a school by school responding to a challenge, an academic challenge. The problem is that one's just about over. I think the deadline is probably past, but it'll be around next year. And so, schools, we've got one. We did high school and college level, 2 levels at the challenge. But we had one grade school in Japan say they wanted to do it. And they said, we need to practice our English, and we'd love to do this. So they don't even want to be in the competition for money, but they want to be in the competition. So we're working with them and, working times and stuff to work with them.
That's great.
So we try to interface around the world and stuff like that. And, that type of stuff.
Exactly what I was wanting to get out there. So no, I appreciate your time, and like I said, we'll post some links, and hey, I'll help try to post what I can about some intern stuff coming up. So appreciate your time. I know there's so much detail to this topic. We honestly could go on for hours, but this has got to be a general overview on a platform like this. But I'll link it all in there so people who really interested can really dig into that stuff. I've been reading it ever since I contacted you a few weeks ago, and it kind of got those juices going again of reading and digging more about it. So it's exciting. That for me it is. And that's why you're on here.
Yeah, we're really pleased with our body of knowledge that's developed on the website www.isic.org. We've got so many papers there. We've got like 900 papers in the references. And we've got 30 or 40 videos in there and stuff like that, and a whole bunch of charts. And then there's just the published articles, like in the Journal of the British Interplanetary Society and stuff like that. So if you're really interested and curious about space elevators, skip everything else. Go to the body of knowledge. It's remarkable what's there.
Thank you. So once again, thanks for joining me and taking some time out and spending it with me. And we'll talk soon, I'm sure. Thank you.
Okay, sounds good. Thanks for the invite.
Yes.
Appreciate it.
Thank you.